Minerals in polarized light, cleavage. In this slidecast, we'll cover using cleavage to help recognize minerals in thin section. You very rarely just recognize a mineral based on cleavage. It's one of the things you use, but it can be really diagnostic. Let's look at a rock. This is a metamorphic rock from Scotland. It's got several different kinds of mineral in. Two of the minerals, muscovite and biotite, have strong cleavage. Quartz in the center of the field of view has virtually no cleavage, and there's also some titanite with a bit of fracturing. Each of them is slightly characteristic. Each of them helps you to recognize minerals. So what's the difference? How do you recognize the difference between a mineral that's fractured and a mineral that's got cleavage? On the left-hand side is a pyroxene. It's got a very characteristic fracture pattern. It's all parallel lines. This is quite a lot of cleavage, even for a pyroxene, but it's diagnostic. On the right-hand side, this is an image of a garnet. It's got fractures. They're sort of randomly oriented. You can't really tell that there's any particular cleavage there. Garnet is characteristically fractured, not cleaved. So let's look at a rock. This is on the virtual microscope site. It's an Essexite. It's an olivine basalt picked up by Charles Darwin. You can see it's a fine-grained basalt with two different kinds of phenocrystin. There are olivine phenocrysts. We're going to zoom in on one now, down here at the bottom of the slide. You can see this olivine is cracked, it's fractured. And in this case, the fractures are filled with a green alteration mineral. It's probably olivine, it's probably chlorite. Here's another one, even more fractures here, sort of randomly oriented, filled with chlorite. Very different. Okay, it's a slightly different color, but look at that cleavage. Strongly aligned in this pyroxene. Further up the thin section, there's some more pyroxene phenocrysts. Again, strongly aligned cleavage. And that oblong one there in the middle looks like it just about has two. There's some fracture in there as well. Now this bunch of crystals, there's one olivine, this oblong olivine to the left. Just above that looks like there's a pyroxene, and to the right some more fractured grains, more olivines. It's a very characteristic difference. What's the reason for that? It has to do with the way that the silica tetrahedra are stacked in the minerals. In this table at the top you can see olivine and garnet. They have isolated silica tetrahedra. They tend to be fractured. They tend not to have cleavage. When the tetrahedra form in single chains, those are pyroxenes, and you typically have cleavage, and in end sections of the pyroxene you can see cleavage almost at 90 degrees. It's quite characteristic. In amphiboles, double chains, they tend to have a different kind of cleavage. They tend to have cleavage at 60 degrees. So there's a difference between the pyroxene and the amphibole. Micas have characteristic sheets of tetrahedra, and they have a very simple cleavage. We'll look at them in a few minutes. Very easy to recognize. When you get to the more complex silicates, quartz and feldspar, that are framework silicates, they have cleavage as well, but it tends not to be as strong as the micas. So you have strong weak cleavage and weak cleavage. Bottom right here you have some biotite and some muscovite, very simple cleavage. Top left is a feldspar. It's kind of mottled and altered, but there's no particularly strong cleavage. You can see an alignment top left to bottom right in that grain. Not very strong. Let's look at another rock. This is a staurolite schist from Glencova. It has both staurolite and garnet in it. It's actually a really beautiful rock. Let's zoom in. So, most of the vertical alignment here is biotite, and you can see in each of the biotite grains cleavage. Straight lines parallel to the parallel sides of the biotite. The biotites are slightly different colours because they're pleochroic. We'll come to that in a different slide cast. But each of them, if you zoom right in, has these characteristic lines parallel to the sides. Now this white mineral in the middle, that's quartz, that has no cleavage to speak of. It has a slight mottling colour in thin section, but you'll never see cleavage in quartz. Also in this thin section, in the view here to the left, you've got a garnet, and to the right a staurolite. They're full of inclusion, so it's not easy to see, but they're fractured. They're not cleaved. Again, characteristic of these minerals. So, cleavage can be diagnostic. It's not the only feature, but it can be diagnostic. This is muscovite, a clear mineral, but it's a mica. It has that single, simple cleavage. Biotite that we've just looked at, again, single, simple cleavage. It's diagnostic of biotite. It's diagnostic of micas. In pyroxenes, like the one that we looked at earlier, you can get one cleavage in longitudinal sections, but if you get an end section, you can see this 90-degree cleavage. You see the pyroxene on the right here has a 90-degree cleavage. It's worth spending a lot of time on a thin section just looking around trying to find these end sections. This is an amphibole end section. Two cleavages again, but they're not at 90 degrees. This time the angle is around 60 degrees. Let's just spend a little more time on that because the virtual microscope allows you to measure that angle. So I'm going to go through a little activity now, and it's worth going to the sections after the end of this slide cast, exploring them and trying this out for yourself. So we're going to go to an olivine pyroxene amphibolite. This is from Scourie in Scotland. Go to the microscope and you can see different kinds of minerals in this section. In fact, there's olivine, pyroxene and amphibole here, but let's focus on the amphiboles. They're the pale green minerals. Don't worry about recognizing them too much at the moment. As you zoom in, you see some of these minerals, some of these grains have cleavage and others don't. To the right, there we go. This one seems like it's got two cleavages. See the angle between those two? And that's not just a freak. Here's another one. Characteristic angle between the two. So let's try measuring them. Click down here at the bottom right. Click once for measure. Click twice to get the angle tool. Now on the section, click and drag parallel to one of the cleavages. It's actually measuring the size of the grain there as well. Click and drag again and it gives you an angle. So the angle between these two isn't exactly 60 degrees, which you might think about. Why isn't it exactly 60 degrees? It's about 53 degrees in this case. Let's try it again. Click, drag. That tells you the size of the grain. Click and drag again. 60 degrees, 61 degrees. So in this case, it was exactly the right angle. There's a reason why those two are slightly different. They're very characteristic. They're both amphibole. There's a little bit of difference that if you think about it, you'll understand why. So, go to the thin sections at the end of this slide cast, take a look at them, explore them, see if you can find end sections, see if you can start to use cleavage to recognize minerals in thin section.